Welcome to the very last talk of our spring series. It's a real pleasure to have Michael Kearns here with us from Penn. Michael was a grad student of Les Valiant's at Harvard, and then he spent the 1990s at Bell Labs, or later AT&T Labs, where for the last 4 years or so he was head of AI efforts there. As you know, there were a tremendous number of interesting people there, and some of them, including Michael, are now at Penn, where he's a full professor and co-director of the Institute for Research in Cognitive Science, which is the closest analog at Penn to CLSP here. He's worked in practically every area of machine learning, reinforcement learning, decision trees, model selection, lots of other things that I'm not mentioning. And in fact, I guess you've done some work recently on dialogue. I was in the dialogue system, so I was interested to say.
It depends on your definition of recent, but yeah.
Well, since 2000, with people like Lynn Walker and Bob Lincoln and Satinder Singh. But what he's going to be talking about today is a really, really interesting line of work, which is not particularly about language, but which touches on the kind of modeling ideas that we've seen in graphical models and brings them to a new area, namely game theory. And I guess this is a summary of some large number of papers in that area. So very much looking forward to the talk. Let's welcome Michael Kearns.
Thanks, Jason. And just to follow up, if this week is your last seminar, then your last one on language was last week. Because as I threatened Jason, the particular thing that I've been working on for the last few years has rich connections to various aspects of machine learning and probabilistic modeling, but is not about language per se, but hopefully you'll be able to appreciate some of the connections. And so as Jason suggested, what I'm going to really do today is survey for you sort of a series of papers that I've written with a collection of talented co-authors that I've listed up here over the last 4 years or so. And the high-level idea is to try to bring to game theory and economic modeling the same kind of power that things like graphical models brought to probabilistic reasonings, and to see where this analogy is both supported and where it breaks down and what the differences are. So let me begin, actually, for this audience by starting with a discussion of probabilistic reasoning. So, all of the time in machine learning and related areas, we encounter the following problem. We need to model a very complex, high-dimensional, multivariate distribution. The dimension is sufficiently high that we don't want to write this distribution in a so-called tabular form, by which I mean we don't, if we have, for instance, n binary variables, want to describe the joint distribution of them as a table of 2 to the n minus 1 entries specifying the probability of each one of those joint settings. And so there, as I'm preaching to the choir in this crowd when I say that there are many, many settings where one wants to model such high-dimensional joint distributions, like the joint distribution between the set of diseases and symptoms, between words and documents and topics, so on and so forth. And a reasonable question to ask that has been asked is, why in the world should anything better than the tabular form be possible? And of course, the answer to that is that luckily the world is not an arbitrary place. It has structure. So in particular in the probabilistic setting, it's not the case that in a typical application that all of the variables will directly influence each other. They might indirectly influence each other, but there will basically be some kind of network interaction structure that you can write down that asserts which dependencies hold and which independencies hold. And the high-level idea is that this should somehow ease the process of both writing the model down and performing the computations of interest, which in the case of probabilistic modeling tend to be those of inference and learning. And this story has essentially been very beautifully played out in something like a 20-year literature that we now call variously by terms such as Bayesian networks, Markov models, or just graphical models more generally. So I'm just going to put up here a few slides of visuals. This is just to visually demonstrate the point that graphical models by now have been applied to a very, very diverse set of applications. So on the left-hand side, for lack of a better term, I'm calling this an engineered application, where in particular here is a little fragment of a Bayesian network for the problem of decoding turbo codes, which is a highly technical engineering problem that is an artifact of a human creation, namely turbo codes. And on the right-hand side, I have a typical diagram from a paper by somebody like Arrow-Debreu, who's trying to apply Bayesian networks or similarly rich probabilistic models to a problem in medical diagnosis. And so, many, many people have kind of come to the table in the statistics and the probabilistic modeling and the AI communities and machine learning to pick up these kinds of models take them to different applications and say, what are the qualitative aspects of independence or dependence that I want to capture, write these structured models down, and then hopefully find ourselves in a position where we have algorithms to manipulate those models in a powerful way. Now, if you step back for a second and you think about what are the domains of science that perhaps the greatest thought has been given to the problem of structure and interaction, I would argue that areas like economics is one of the oldest areas where there's been some acknowledgement historically that there are various asymmetries in the interactions between a large number of parties, right? And it's essentially the asymmetries that are being captured in areas like Bayesian networks. By asymmetry, I mean that not everybody is connected to everyone else, and you can exploit that asymmetry. So here, for instance, I've just shamelessly stolen from the web, which is quite easy to do these days, a number of visualizations of different kinds of networks. So here, for instance, is a diagram that's visualizing world trade as of the year 2000, I think, where each vertex of this network is a sovereign nation. And essentially, there's a link between two sovereign nations if they had some non-trivial amount of foreign exchange between them in the year that this diagram was created. It's not easy to see from where you're sitting, but if you looked at this diagram carefully, you could see that this is in fact not the complete network. There are definitely pairs of countries which are not connected in this diagram, and there's a variety of reasons that you might imagine that such asymmetries arise, including things like embargoes on trade or other sorts of regulatory restrictions or even geographical constraints. This is also a famous diagram due to Valdes-Krebs, in which each vertex in this network is some internet industry company circa roughly 2000, and there's an edge between two vertices if at that time those two companies had some kind of formally declared strategic alliance or other contractually specified business venture. So this is what you might think of as an economic or a corporate network. And some of you may be familiar with the fact that many people are actually starting to seriously take a look at the internet as not just a technological network, which of course it is, but also an economic network, and trying to think about how the structure of that network plays out in different kinds of economic protocols. In particular, people look at problems like routing or other kinds of congestion control problems as an economic problem in which a number of parties are competing for a finite resource and will essentially behave in something akin to a game-theoretic manner in that they will choose to change their behavior if there's some benefits to be accrued to them individually by doing so. So all this stuff is very, very much in the air these days. And I've just written down here a very short list, I'm sure you can make up many more and many better ones, of examples where structure arises in economic and social analysis. What are some of a partial list of the reasons why it's the case that not everybody interacts with everyone else, not everybody can trade with everyone else, so on and so forth. So for instance, you of course have trade agreements and restrictions between countries. You just have social relationships between business people. If you're a salesman for a product, you can sort of only sell to people that you know about, and you can't sell to the people that you don't know about. Of course, on Wall Street, there are all kinds of regulatory and reporting and organizational restrictions that hold, and on and on and on and on and on. So there are many, many reasons why in naturally occurring social and economic networks there's some non-trivial structure. And so the high level, the overarching goal of the line of research that I'm going to tell you about is to develop what you might, in analogy with probabilistic reasoning, think of as strategic reasoning. And so I'm going to start to draw a metaphor here that will take us a certain distance and at some point break down, but it's actually interesting how far you can go. In strategic reasoning, rather than thinking of the variables as being random variables, you should think of them as being players in a game or other entities in some kind of economic or game theoretic setting, organizations, firms, countries, what have you. And I'll give specific instantiations of all these ideas as we go. And the interactions between these variables, rather than being governed by the laws of probability theory and statistics, are governed by the laws of self-interest, namely rationality. So the basic computation you like that a vertex does, rather than sort of computing its conditional based on the behavior of its neighbors, it computes what we would call in game theory a best response to its neighbors. It optimizes its own return or utility in response to the behavior of its neighbors. And so the foundations of this entire area, rather than being those of probability theory and statistics, are going to essentially be those of game theory and mathematical economics. And the goal, of course, is to replicate the power of graphical models from both a representational and algorithmic standpoint for problems of strategic reasoning. So I'm going to try to quickly go through three main topics that we've worked on in this general area over the past few years. The first is the most basic, where essentially we're trying to do for game theory what Bayes nets did for probabilistic modeling. And this is the topic I'll call graphical games, and the particular algorithm, the most basic algorithm which you can think of as the analog to the so-called polytree algorithm or junction tree algorithm for graphical models for probabilistic reasoning that we call Nash prop, which is short for Nash propagation. Perhaps the point where there's the deepest and I think closest relationship between the game-theoretic view of networks and the probabilistic modeling view of networks is on the topic of correlated equilibria, which is a lesser-known notion of equilibria than Nash equilibria, which I'll describe to you, and which there's a very interesting relationship between a graph or a network viewed as describing the strategic interactions between many parties in a game, and the minimal model you need to represent the correlated equilibria, which are essentially a joint distribution which might allow high-order correlations. And then towards the very end, I'll spend a quick amount of time telling you about very recent work, rather than working in the very general framework of game theory, is looking at market economic models and what happens in particular when those economic models are merged with some of the universal properties that people in social network theory have identified in recent years. And please feel free to, in some sense, there's just too much stuff in this talk anyway, so it doesn't matter if I finish, so feel free to interrupt me and however far I get is how far I get. Okay, but let me begin with graphical games and Nash propagation. So let me first just give a 10-cent introduction to game theory, and both just to do something different and also because it'll be useful later, rather than doing the standard prisoner's dilemma, I'm going to do the two-player game known as Hawks and Doves. So in this two-player game, there are two players. There's a player that gets to choose the row, and there's a player that gets to choose the column. And I've indicated in this table for each choice of the joint actions what the payoffs to the two players are. And so here's the little story, as in there's always a little story that goes behind a game theoretic matrix. Here's the story that goes behind this little matrix. There are two parties that you should think of as equally matched that are fighting over a valuable and scarce resource. And the value of that resource is V. And the players have essentially two strategies available to them. They can either be passive and submissive, i.e. play the dove strategy, or they can essentially put on a display of aggression, which we'll call playing the hawk strategy. And so let's just kind of work through the numbers here. So if, for instance, the row player chooses the hawk strategy, the aggressive strategy, and the column player plays the dove, then the hawk walks away with the entire resource of value V, and the dove gets nothing. Similarly, in the symmetric corner down here, if the row player is playing hawk and the column player is playing dove, then the hawk player walks away with the resource and the dove gets nothing. We'll assume that the resource is divisible, so if both players play nice, i.e. they both play the hawk strategy, then there's a way for them to split the resource and each receive value V over 2. And then the interesting entry in this matrix is the one in the upper left-hand corner, where we assume that if both players put on a display of aggression, it will actually escalate to a fight, that the parties are equally matched, and so you have a 50% chance of winning the fight and gaining the resource, which has value V. You have a 50% chance of losing, and then losing the cost has cost C. And the general assumption in Hawks and Doves is that the cost of losing a confrontation is larger, perhaps much, much larger than the value of the resource being fought over. So think, for instance, C being the cost of being the victim of a nuclear first strike, and V being, the strategic value of getting some small South Pacific island. This is the kind of reasoning that people seriously did back in the highest level of governments back in the early 60s. It's not clear that we're much better off now, but in any case, so in that particular case, each player has expected payoff 1/2 V minus 1/2 C, and since C is larger than V, this is a negative number, okay? So game theory, in its basic form, writes down matrices like this and says, what should two rational parties do if confronted with this game, okay? And I'll define formally the notion of Nash equilibria in a minute, but informally it simply means a pair of strategies, a strategy for each player with the property that neither of the player has a unilateral incentive to deviate, i.e. both parties are playing optimally with respect to what the other party is doing. Doesn't mean that they couldn't both benefit by doing something different together, but you only look at the unilateral improvement in your payoff that's possible. Okay, so in this particular game, it turns out there are 3 Nash equilibria. One of them is hawk-dove, and the other is dove-hawk. So let's just go through one of these. So if you're absolutely convinced that I'm going to play hawk, and you're the column player, so if you know that I'm going to play hawk, then your only choice is between playing dove and getting 0, or also playing hawk and getting V minus C over 2, which is a negative number. So you're going to go ahead and choose dove. Similarly, if I believe or know that you're going to play dove, then my choice is between getting V over 2 or V, and of course I'm going to play V, and that's why this is an equilibrium. Okay? So these are 2 deterministic equilibria. There's also a probabilistic equilibria in which both of us randomly play our Hawk strategy with probability V over C, which is a number less than 1 since V is smaller than C. And it has the interesting property that, of course, that if the cost of losing a battle is much, much higher than the value of the good, then naturally we're going to play our Hawk strategy with very small probability, but as V approaches C from below, then we'll be fighting all the time, okay? So this is, of course, a little bit harder to verify is a Nash equilibrium, but you can kind of work through the algebra and it's pretty simple. So this probabilistic equilibria in game theoretic terms is often called a mixed strategy because it's essentially a convex combination of the pure or deterministic strategies. As an example of just an everyday children's game in which there are only mixed Nash equilibrium, think of the classic game of rock, paper, scissors, where essentially the only equilibrium strategies are where both of us truly randomize over our 3 actions. If you do any deviation from playing a third rock, a third paper, a third scissors, then you have to be playing one of those things with probably greater than a third, and I'll just play the single strategy that dominates that, and so that can't be an equilibrium. Any questions about this?
That's actually not true.
What's not true?
I think that you can vary the rock, paper, scissors, and you can vary pretty much.
So if you're talking about behavioral considerations, that might be true. But in the mathematical language of game theory, the only equilibrium of rock, paper, scissors is a third, a third, a third. Right? You're not questioning the definition of Nash equilibrium, right? Okay. We can discuss behavioral issues, which are interesting to consider as well. So these are the basics of game theory. The basics of multiplayer game theory essentially just generalize the situation I described. Rather than 2 players, we have n players. Think of n as being large. Think of n as being like the number of variables in a large network, okay? Each player has some number of actions, 1 through k. Think of k as being small, like, playing hawk or dove, okay? That's not to say that it's not interesting to think about k being large, but essentially all the results I'm going to describe in this talk mainly say something interesting about the regime where the number of players is very large, and I don't have anything special to say about the number of actions, so we may as well think about it as being some fixed small number. A sub I is the particular action chosen by player A. The vector A is the population joint action, it's the vector of all n of our actions. And basically, the game is described by a set of tables or matrices that for each player I describes m sub I of A. So the important thing here is that this matrix is indexed by the entire joint action of all of our play, describes what my payoff will be. Okay, very, very rich formulation, lots of things you can write down as very high dimensional rich games. Note, the very simple analogy I'm offering here is this is like representing a probability distribution in tabular form. Right? There's sort of no structure or assumptions here whatsoever. Even in the smallest variation in somebody's action, everybody's payoff could change wildly and in an unconstrained fashion. And of course, writing down this table is an affair that's exponential in the number of players involved. So even if each of us only has 2 actions available, but there are n of us, there's 2 to the n entries in each one of our tables. Okay, but that doesn't stop us from defining Nash equilibria. A Nash equilibrium is a choice of mixed strategies for each player. So in the language of probabilistic modeling, this is not only a joint distribution over all of our play, it's a factorized, it's a product distribution. So a Nash equilibrium is a choice of a probability distribution over each of our action sets. And so that the joint distribution is just the independent draws from each of our distributions. So it's a factored model, it's a highly constrained distribution that has the property that no player has a unilateral incentive to deviate, i.e., if I believe that all of you are going to play an action drawn from your prescribed distribution in the proposed Nash equilibrium, that in fact my going ahead and playing my proposed component of that joint distribution is in fact a best response. It gives me the highest expected return. And of course, you can write down the equation for this, but I won't bother, okay? So a mixed strategy is a product distribution over our joint action space so that no player has a unilateral incentive to deviate in terms of improving their expected payoff. And the classic Nobel Prize winning theorem of Nash from the early 50s is that for absolutely any game, a Nash equilibrium exists. And that's a great thing. More irritating is the fact that there might be many of them. And in fact, not only might there be many of them, but the number of them might be exponential in the number of players involved. And to make matters worse, they might be incomparable. So it could be that there's many, many Nash equilibria, and in some of them I get a high payoff, and in others I get a low payoff. So I actually, if it were just left up to me, I would prefer that we all play the equilibrium in which I get the highest payoff, but of course you may not want that, okay? So these are issues that we'll discuss as we go through. Okay, any questions though? Yes?
Just so you don't assume that each player knows what they are playing, assume that there is some order in the way you play.
So Nash equilibrium is a static descriptive notion. It basically says, you know, given any game, you can ask the question, what are the equilibrium points, in the sense that it's a set of behaviors for everybody such that no party will want to change their behavior, okay? It doesn't answer in and of itself how it might be that, you know, naturally playing players might converge to an equilibrium, or if they do, which equilibrium they'll converge to. There's gargantuan literatures on those topics, and there are interesting questions that arises from that gargantuan literature intersected with what I'm going to talk about today, but I'm not going to talk about that because it's a complex can of worms. The literature on learning in games is a very, very active area of research in game theory, and it has been highly inconclusive in my view until possibly the last couple of years, where there have been some very nice breakthroughs, and I can sort of describe those offline. Okay, but at a high level, you can kind of see where I'm heading here. You know, this is the basic description of a game. An equilibrium always exists. It's sort of an inconvenient way of representing a game because there's no way of writing down structure, and it's exponential in the number of players. And one thing that is a bit of a difference compared to probabilistic inference is that if I just, you know, if in probabilistic inference, if I just ask the question, well, you know, what's the conditional distribution on this variable given the setting of some other variables, there's a unique answer to that. Here you might suspect that things are going to be a little different just because there are so many solutions to the basic problem of what the equilibrium points are. Okay. Computational status. So the computational status of computing a Nash equilibrium, by which I mean the input is a game described as these payoff matrices, and the output should be some Nash equilibrium, let's say. The computational status of this is murky, by which I mean that it's not known to be in polynomial time, and also not known and probably unlikely to be NP complete. So it really is one of these border problems that it's hard to know which way it's going to go. But it, you know, at this point, it's hard in the sense that there's no known polynomial time algorithm, and not for lack of smart people thinking about it. Okay, so you know, what a good AI person wants to do when looking at that situation where you've got many, many years of smart algorithmic people trying to bang their heads on the problem is to solve a different problem by changing the representation. And I think in this case that there's a clear reason to do that, in the same way that there was for graphical models for probabilistic inference. So we're just going to introduce an undirected graph G that's meant to capture local or local strategic interactions. Each player is represented by a vertex in this graph. And I'll use n sub I of G to denote the neighbors of I in the graph G, which by convention will include I itself. So the neighbors of player 2 in this graph are 1, 3, 4, and 2 itself, but not 5, 6, 7, and 8. And the basic semantics or assumption we're making here is that the payoffs of the game, rather than needing to be written as tables which are indexed by the entire joint action, only need to be indexed by the joint actions of the local neighborhood. So nothing could be more natural, right? So we're going to assume that the payoff to player I is expressible now as a matrix m sub I of A prime, where A prime is just a joint setting of only over the variables in the neighbor set of G. So this is exactly analogous to kind of, you know, the graph structure plus conditional probability tables or potential function in the undirected case for probabilistic modeling. The entire representation consists of the graph plus these local game matrices, which is entirely analogous to the separation of the qualitative and quantitative aspects in probabilistic modeling. So it's analogous to the graph plus the condition of the CPTs or potential functions. Like those representations, this one, rather than being exponential in the number of players, is exponential in the maximum degree. So this is a win exactly to the extent that when you write your network structure down, there's some non-trivial reduction in the degree of players. Like not everybody interacts with everyone else. You can also imagine, and people have, the marrying of this idea with the idea of parametric local game matrices in the same way that people in Bayesian networks don't just introduce the network structure, but often to deal with high degree in that network will introduce something like, you know, a sigmoidal transfer function for the conditional probability tables. And I won't talk about those you know, extensions, but you can imagine them. Okay, now, all I've done is introduce a new representation for games. And in fact, any game can be represented in this model, right? I can just let the graph be the complete graph. So everybody is still connected to everyone else. These local game matrices become the global ones, and I haven't gained anything. So equilibria, of course, still always exists because this is just another way of writing down the game. And as such, you should also understand that since you can represent the original problem in this model, from a computational perspective, this can't make the problem any easier, right? But what you can now naturally ask in this setting is there special structure? Just as with Bayes nets, the general problem of inference is intractable. In fact, there it's even known to be intractable in specific ways, unlike in game theory. But the basic idea here is to look for special structure that would permit some kind of algorithmic exploitation, this time in a game theoretic context. Okay, so I'm not going to go into great detail on this, but sort of the first foot in the door we got in this direction several years ago is what I call the Nash crop algorithm, which you should think of at a high level as the analog to something like the polytree algorithm. And I'm going to briefly describe how it would work, and I'm going to describe how it would work in the case where the graph is actually a tree where you can prove some rather strong things about it. And I'm going to try to highlight primarily what's different about this setting than the case of, let's say, the polytree or junction tree algorithm. So the high-level idea is that, you know, we have a tree here, and we have some vertex v, and I've oriented the tree so that the root is down here somewhere. And so v has one downstream neighbor, which I'll call w, and 3 upstream neighbors, which I'll call u1, u2, and u3. And the basic idea is that if we assume that, let's just assume that we're in the binary action case, so that the mixed strategies of each player can be just described by a single number between 0 and 1, which is their probability of playing their first action, and then 1 minus that probability is the probability that they play their second action. So the high-level idea here is that what V would like to send to W is a table. Okay, so I mean, by the way, I mean, I know that everybody in the audience will understand when I say this. We're essentially going to try to turn this into some sort of dynamic programming problem. And the question is how exactly do we go about doing that, and what is the form of the dynamic program? Okay, so I'm going to first describe the dynamic program in a way that won't obviously be implementable, and then I'll describe to you quickly how you can fix that problem. So basically, what V would like to send to W is a table which is indexed by all of the real valued probabilities that V and W could both be playing. So problem number 1 is that this table is sort of an infinite object, right? It's indexed by 2 uncountably infinite values of V and W between 0 and 1, and I'll describe how we get rid of this in a second. But the definition is well defined. So basically, W, for each possible value of what W might play little w and what V might play little v, the table T of WV is either going to be 0 or 1. And it's going to be 1, essentially, if and only if there's some upstream Nash equilibrium in which V plays V given that W equals W. So what do I mean by that? I mean that we take these two values, W and V, and we clamp W to be playing little w. Since this is a tree, when we clamp W to be playing little w, whatever else was down here is now irrelevant to V because it's now separated from the rest of the graph by the fact that we've conditioned on the value that W is playing. Now, if we simply condition W to be playing some value like 0.1 and ask, is there a Nash equilibrium for the tree upstream condition on that? Of course, the answer to that is trivially yes, because that's just another game and it always has some Nash equilibrium. But if we condition on whether there's a Nash equilibrium in which V plays some particular value, then the answer might be yes or no. Okay? So basically, we want this table to contain a 1 if and only if, conditioned on W playing little w, there's an equilibrium upstream in which V plays V. And the nice property about this definition is that it's inductive, right? Basically, there's going to be such an equilibrium only if there's some way of setting the values for U1, U2, and U3, which have the property that they all told V that they could play that value if V played little v. Okay, and now we basically, in probabilistic modeling terms, we've now fixed the Markov blanket of V. We've entirely isolated V from the rest of the graph by the conditioning of W playing little w and searching over all values for the parents of V, which is where the exponential in the degree is going to come in. Okay, and now there's one last thing we have to check. We have to check that once we fix all those values, that V playing little v is actually something V would want to do. That it's a best response to its local neighborhood. Okay? Okay, so this is the high-level idea. This problem of the fact that the tables that I've described them don't even have a finite representation is a real problem. And if you try to turn this into an exact algorithm, you can't easily do it. The combinatorics, essentially the representational or descriptive complexity of this table can grow exponentially with the depth of the tree. However, there's a nice discretization lemma you can prove, where essentially if you only look at values for W and V on a sufficiently fine grid, then you can compute approximations to Nash equilibria. And the nice thing about that lemma is that the resolution of that table, the resolution of the discretization, only needs to sort of scale inversely with something exponential in the degree, and not something exponential in the size of the graph. If it was exponential in the size of the graph, then we do this nice discretization scheme, but then we'd have to search over these tables that were back to exponential in the overall size of the network, and we wouldn't have gained anything. The nice thing is that, and intuitively this makes sense, you're only going to be looking at kind of products of probabilities in the local neighborhood, so you should only need resolution that has to do with how many variables there are in that neighborhood, okay? One nice thing about the algorithm, the approximation algorithm, is that in fact what you get at the end is this distributed lattice, if you like, or trellis, in which all Nash equilibria, or an approximation to every Nash equilibrium, is represented. So even though the number of Nash equilibria might be exponential in the size of the network, what you essentially get is this distributed representation where at the root, essentially at the root, all the root knows, there was no downstream child there. So the root basically knows all the different values that they could play that can somehow be completed to a global equilibrium upstream. And the root can then just sort of non-deterministically choose one of those, inform all of its parents which choice it made. They can then make non-deterministic choices about what they play. And each one of these non-deterministic paths corresponds to a different equilibrium. So this is very much like in Viterbi decoding, the fact that you have a compact representation for an exponential number of solutions. There's something very analogous going on here. Okay. Now, so basically, you can prove very nice, strong things about this algorithm in the case where it's a tree. What one would like to do, of course, is to generalize this to arbitrary topologies. And again, in exact analogy with what went on in Bayesian networks, there are essentially two main routes you can take to get this to be a heuristic on a graph with arbitrary topology. One of them is sort of the junction tree and cut set idea, i.e. you take something that's not a tree and you perform various graph-theoretic surgeries on it to turn it into a tree, and the cost of that transformation is going to somehow be exponential in how many bad things happen to you on the way, right? So what was the size of the largest what was the size of the largest clique set, the cut set you had to look at? What was the size of the largest mega node that you merged together to turn it into a tree? It'll be exponential in these things. So that's one route. The other route, of course, is sort of the belief propagation route, which is you just sort of define the algorithm for arbitrary topologies, forget the fact that there are cycles in it, and hope that everything works out. And of course, there's a rich literature in the Bayesnet community on how often that works out well. Okay. And so what we call Nash prop is just the generalization of this algorithm to the case where you have an arbitrary topology. And I won't go into the details, but at a high level, all you do is, now you're going to have an algorithm works rather than in a single forward pass and backward pass in the tree. Now it's going to be an iterative algorithm. At each iteration, every node receives messages of this form from all of its neighbors. And then it's going to send out messages to every one of its neighbors by successively pretending that each outbound direction is in the direction of the root of the tree. Okay, so it's going to basically, first pretend that W is in the root of the tree and do this computation. Then it's going to pretend that U3 is in the direction of the root and that U1, U2, and W are the parents, and just do this algorithm in all those directions. So, just as a quick visual, we implemented this algorithm a few years ago and played around with it on some simple games. These diagrams here, so this is the graph of the game. I won't tell you what the payoff matrices are, but it's sort of a simple game in which there are two types of players, those that want to try to have their action agree with what their local neighborhood is doing, and those that want to disagree with their local neighborhood. And these little diagrams on the side are actually showing what these tables look like. So these tables run from 0 to 1 on one axis and 0 to 1 on the other axis for the probabilistic strategies of the two players, the biases, if you like. And the black area is showing where the table has a 1 value versus a 0 value. The only point of this diagram is to sort of go back to the point I made before, which is that even in rather simple games, you can very quickly get some rather complicated messages being passed back and forth between these things, which is sort of why you need this discretization scheme. Because if you really try to describe these diagrams in a precise way, that just the descriptive complexity of them is growing quite rapidly. Let me skip this in the interest of time and go to this diagram. And so, again, I won't go into detail on this diagram, but we actually, as people have done for belief propagation in Bayesian networks, we implemented this algorithm and tested it on a large number of rather loopy architectures that were deliberately designed to have enough cycles in them that the traditional cut set or junction tree approaches would be losing propositions. And the only point I would want to make in these diagrams is that here on each axis, the number of players is growing. Here, computation time is being measured. And in general, you're seeing something not far from a linear dependence here. And in some sense, this is a great advance for game theory, because if you just take the traditional way of representing games and the traditional way of computing on those games, you could never do computations on non-trivial games that had hundreds of players in them. And there's no magic going on here other than the magic of identifying that there's a network structure and deliberately exploiting that network structure in your algorithms. And I think that this is a direction that areas like game theory will be using more and more as they become aware of the existence of these kinds of models. Okay, so let me move to the second topic, which, as I mentioned before, I think is where the connection between the game theoretic aspects of graphical modeling and the probabilistic aspects have a very sort of clean, nice connection. And it'll also require me to explain this notion of correlated equilibria. And I think I'm one of the growing number of people who really think that there are many reasons to think of correlated equilibria as the more natural and important notion of equilibrium compared to Nash, which is the one that everyone knows about. But I think that's changing. So what is a correlated equilibrium? So recall that a Nash equilibrium in probabilistic terms is a product distribution over our joint action. And that the reason Nash considered product distributions was because it was the minimal class of distributions over our joint action required to prove the existence of equilibria. So he sort of needed to go to convex combinations of the basic strategies, but no further, and that's why he stopped. This was sufficient to prove existence of equilibrium. So just humor me for a minute, and I'll describe in a minute. Let's just imagine now that we're actually going to allow an arbitrary distribution over our joint action. So remember now, think of A as being a binary vector describing what our choice of actions is. And now P of A, rather than being a factor distribution, is an arbitrary distribution which might have very, very complex higher-order correlations between different sets of us. Okay? So I'm now going to describe what a correlated equilibrium is. So in a correlated equilibrium, there's several ways of describing it, but this is, I think, one of the more natural ones. Suppose that we have this, you're all playing this game, and I have this joint distribution in a box up here. And I'm going to draw a joint vector A from this distribution, and I'm going to put in a little envelope for each one of you, your component A sub I. So I tell you what action you should play according to the specific draw I made from the joint distribution P. Now remember that in the case of a Nash distribution, where this distribution factored, you're receiving your little envelope telling you to play 0, for instance, would have no information whatsoever. It wouldn't condition your beliefs about what everyone else was going to play because it was all independent. Now that's not true. The fact that you've been told to play 0 might condition your belief about what other groups or individuals might play. And so you might now think about cheating, right? You might be thinking, well, now that I know that the draw from the distribution was 0, maybe you know something like, I know that lots of other people are going to be playing 1, and it's good when they play 1 that I play 1 also. So even though I was told to play 0, because that conditioned me to know that a lot of you were playing 1, I'm now going to cheat and play 1. So that's what's not a correlated equilibrium. P is a correlated equilibrium if conditioned on everyone else playing their part of the joint distribution given what you were told to play. Going ahead and playing that conditioning event is still optimal for you from the viewpoint of expected return. And again, I won't write down the equation here. So it's just like a Nash equilibrium. Nobody has a unilateral incentive to deviate, but now there are correlations between the actions available. Okay? And it's easy to convince yourself that this is exactly just the Nash definition when you have a product distribution. An alternative interpretation of a correlated equilibrium is that in a standard equilibrium, every one of you has private randomization available. You can flip your own private points to decide what action you're going to play, but that's it. Whereas in a correlated equilibrium, you're still going to be allowed your private randomization, but I'm also going to pull a coin out of my pocket and flip a bunch of coins and just write them up on the blackboard, and anybody who wants to can have a strategy which conditions their action both on their private random bits and their public random bits. So the everyday example of this is the traffic signal. Okay, so imagine that you have an intersection in the middle of Kansas where there are high cornfields everywhere. And it's a blind intersection. So in order to see whether there's a car coming on the orthogonal road, you really have to get right up, slow down, look both ways, and see that it's clear. And suppose that the actions available to the two players are to, slow down, yield, look in both directions, and then if it's safe, go through, or to just step on the gas and fly right through. Okay. So if you write this down as a matrix, it would actually look very much like the Hawks and Dove games, right? Basically, if you slow down and yield, my best response, of course, is to fly right through. I don't want to wait. If we both slow down and look both ways, we might have some small regret because given that Fred slowed down and looked, I now wish I'd run through the intersection. But then there's this large negative payoff for both of our flying through the intersection. And so the only Nash equilibrium are going to kind of be the ones that I described before. So the traffic signal, though, gives a shared bit of randomization that's posted in the sky available for both of us. And it lets me articulate a strategy now. So now I can articulate the strategy that says, well, if the light is showing green to me, then I'm stepping on it, and if it's red, I'm going to slow down and yield. And it's easy to convince yourself that in terms of expected payoff, given that that's my strategy, your optimal response to that is to take the complementary part. And this gives a new outcome, right? Because this now splits the waiting time before us in a way that you just couldn't accomplish via the more competitive, uncorrelated notion of Nash equilibrium, okay? Okay, so there are many advantages to correlated equilibria. First of all, they can be easier to compute in certain settings, but I think that more important than the technical advantages are the conceptual ones. Namely, correlated actions are a fact of the real world, right? In almost any setting where you really want to model game theoretic behavior, there are correlations between the actions of the parties involved. And so it doesn't make sense to start off with a notion of equilibrium which forbids from the inception the idea of those correlations. And again, in the interest of time, the other one I'll mention is that, getting back to this question about learning, it appears that if you look at a wide class of natural dynamics for how players adjust their behavior in response to each other in learning in games, those dynamics almost never converge to a Nash equilibrium, and there are rather weak conditions under which they will converge to a correlated equilibrium. For reasons I won't describe in detail, but it seems that the correlated equilibrium is the natural convergence notion for lots of different types of learning mechanisms, and Nash is not. So that's, I think, another conceptual advantage of correlated equilibrium. Okay, so those are the advantages, but we've also introduced a problem by going to correlated equilibria as well, which is a representational problem, because before, if I had a multiplayer game, however I was representing the multiplayer game, however hard the search for a Nash equilibrium might have been, at least I knew that the object I was looking for had a short description. So it was just an assignment of the probability to each of the n players, so it was essentially size linear in the number of players. It might have taken me exponential time to find that solution, but the thing I was looking for itself was simple. Now I've opened up this can of worms in which I've said, well, now let's entertain the idea that absolutely any joint distribution might be a correlated equilibrium. And so now I have this problem of how do I wrap my hands around representing all of those different distributions? Well, you can guess where this is headed, right? Because we also have these rich models for compactly representing probability distributions from probabilistic reasoning. And so a natural question to ask is, what's the relationship? And so I'm going to just quickly describe that, and I'm going to say it in English. So let G be the graph of a graphical game. So what we've been talking about so far. We have some undirected graph representing the strategic interactions for the players in a multi-party game, and the local game matrices give the payoffs to the players in that game in terms of their neighbors' behavior. So consider taking that same graph and now interpreting it as a Markov network. And we're basically going to form we're going to take that graph G, and we're going to form a Markov network which needs to add a few edges, but not too many edges. And in particular, you're only going to add local edges. So we're essentially going to form cliques of the local neighborhoods of G. So in particular, one of the things we're going to do is kind of moralize, right? So we're going to take a vertex, and we're going to make sure that all of its neighbors are actually in a clique with each other. But this is only going to add local edges. And of course, once we've done that, we have a new graph that I'm calling Mn of G, which is closely related to the original graph except for the addition of these local edges. And of course, as usual, we can introduce a potential function on each clique in this Markov network. And we can now ask the question, what classes of distributions can this model represent? So the theorem, which I think is quite natural and interesting, is that for any graph, for any game with a graph G, and any correlated equilibrium of that game, there is a correlated equilibrium that is essentially equivalent up to payoff equivalence that can be represented in this Markov model. So in other words, it's saying that the same graph, basically, that represented your game is sufficient now when it's simply interpreted as a probabilistic model to represent all of the correlated equilibrium of your game. And so one of the things that's quite interesting about this is it's a direct link between this notion of strategic reasoning and probabilistic reasoning. In particular, you can read off all kinds of non-trivial dependencies or independencies from this. So for instance, if you take any distant players in the original game, and you take a set of players that cuts the graph between players A and players B, you can immediately infer from this that in any correlated equilibrium, the actions of players A and players B must be independent given the players in the cut set. And so I think that there's a lot of rich kinds of economic and strategic reasonings that can be had by importing the rich semantics we have for independence in graphical models for probabilistic reasoning into game theoretic contexts. Okay, let me move to this last topic. So, I was sort of working on this line of research that I've described for a few years, and one of the things that was a little bit frustrating about it is because game theory is so general, and because the idea of network structure is so general, it was sort of hard to find interesting specific questions to ask or interesting specific models to look at. So of course I could go off and define some kind of game and say, well, here's the game, and here's the network on which it takes place, and here's what happens at equilibrium, and here's how you compute it. But in general, unless I wanted to look at something like multiplayer's prisoner's dilemma, there aren't a lot of benchmark games in game theories that people standardly look at, especially in the multi-party setting. And when I started looking more at the literature on economics or market economies, I realized that here was a rich class of games in which not only is there intense study on the mathematical side, but there are all kinds of popular notions that are closely related to the set of games that are called mathematical economics. So in particular things, anytime you hear a discussion about efficient markets, for instance, and whether the financial markets are efficient, you essentially have a popular notion which is grounded in some very specific game theoretic setting that I'm about to describe. And so what I want to just do now is tell you about some recent work we've been doing at marrying these economic models with all of the work that's gone on in social network theory, identifying certain universal properties that seem to hold in typical economic networks. Okay, so first let me just describe at a high level market economics. Suppose that we have a bunch of different goods. Just think of these as abstract commodities, things like wheat, rice, paper, raccoon pelts, matches, grain alcohol. But I'm sort of thinking of these colonial trading post kinds of entities that essentially there are no differences or distinctions within a good. Rice from one party is indistinguishable from rice from another party. So what we would truly call commodities. So imagine a setting in which we all have different initial amounts or endowments of these goods. So for instance, I might have 10 sacks of rice and 2 raccoon pelts. You might have 6 bushels of wheat and 2 boxes of matches, etc. And basically, the interesting setting is where we want to engage in trade, where what we start off with is not what we really want, and what we want to do is somehow sell what we have in order to get cash and then use that cash to buy back the things that we really want. So, in particular, I might not want or be able to eat 10 sacks of rice, and in any way, if I wanted to cook the rice, I'd need some matches to light a fire. So I want to engage in some trade with you for rice and matches. You might be getting cold and you need raccoon mittens, so you want to buy my raccoon pelts. And so in general, of course, we're going to encode all these preferences or needs as utility functions. And so I won't write down the math of it, but in general, we're going to have some for each one of us rather than a payoff matrix describing what we get paid based on the actions of other people. Now we have a function which is indexed by the amounts of goods that we have, and it just simply describes in a single real number the utility that we give to that particular bundle or package of goods. Okay? So the high-level question here is that if we all have these individual utility functions which express our preferences for different packaged bundles of goods, how should we engage in exchange? What's going to happen? How will we actually engage in exchange? And in particular, what should the rates of exchange be, right? So what should the going rate for 1 box of matches for raccoon pelts be? And this is, these rates of exchange are what we would typically call prices once one introduces the notion of cash. So these are obviously among the oldest questions in economics, and what I want to do is sort of imbue them with a network flavor. But first, let me just quickly describe what's meant by equilibrium in such economic markets. So suppose we have these K goods, and that we somehow magically,
Excuse me,
yeah.
What does the word, I know what it means in normal, right? In normal economics, what does rates of exchange mean in this case?
So rates of exchange would mean ratio for every pair of goods. What's the ratio at which good A should be? How many? What's the cost in units units of good B for each unit of good A? Okay.
So it's just the price. I mean,
Well,
it would be indexed by the price.
No, actually, so actually, the word price implies money. Okay. So I mean, actually, the great invention. I mean, one of the great inventions that is cash is that it takes you away from having to have basically order K squared rates of exchange and encodes all of those in basically K numbers. I mean, this is a very computer sciencey view of why prices. One reason why prices are a good thing. But you could imagine talking about everything that I said so far without ever introducing cash and just having pairwise rates of exchange. How many boxes of matches per beaver pack or whatever. Okay.
But would there have to be a price solution to this problem?
Okay, well, let me go through this because.
No price.
So basically, as I'm about to describe, under suitable conditions, there will always be a magic notion. There will be magic prices at which a good thing happens, which is called equilibrium. Okay, so let's imagine that there is a notion of cash, and imagine that we posted prices for the K goods. So P1 through PK is how many dollars per unit for the ith good. Okay, so you can think of it as I said, prices and cash encoding rates of exchange. So there are sort of two things you want to happen in the equilibrium. First of all, you want all consumers to be rational. So what do I mean by rational? So if we somehow announced prices for the K goods, what every consumer would try to do is they would first attempt to sell their endowment, right? So they're given initial amounts of all the different goods. The first thing they would try to do is just sell their initial endowment at the announced prices. So they would provide supply to the market by trying to sell the goods that they had in their initial endowment. And if they were successful to sell all of their endowment at the posted prices, the cash they would get in return is E dot P, right? The amount they had of each good times its price, okay? Then, with that amount of cash that they got from the sale of their endowment, they're going to go back into the market now and try to buy from the people that sold their endowments a package of goods that maximizes their utility subject to their budget. Okay, so they're going to attempt to buy that package of goods, that amount of goods xi for each good I, that maximizes whatever their utility function is, subject to how much cash they have. So it's a constrained optimization problem. Okay, now. Two things could go wrong with what I just described. Thing one that could go wrong is that some consumer, when they try to sell their endowment at those prices, there's nobody that actually wants to buy all of their wheat at that price. Okay? So that would be that there's excess supply in the market of some good. The other thing that can go wrong is that after everybody sort of sells their endowment, there's somebody who wants to buy, too much of some good and furthermore has enough money to buy that amount of that good at the posted prices, but the supply is not there in the market. Okay, this is excess demand. So basically, at market equilibrium, every individual should be able to be myopically behaving in this self-interested, optimizing fashion, yet the market should clear. Supply should exactly balance its demand. So we basically say that the prices are in equilibrium if there are exactly enough goods to accomplish all these supply and demand steps. So the supply balance exactly balances the demand in every good. Any questions?
The prices P must be related somehow to the utilities, right?
Yeah, absolutely. Right. So there's a complex interaction, right? There's a complex interaction going on between the utility functions and the prices. Yeah.
Someone absolutely has to have some, like they do this differently there, like absolutely needs water or something.
Well, if they have the money to pay for the water, then everything's fine. I mean, yeah, I mean the market doesn't care.
And will it still reach equilibrium if there is some player like that?
So, I mean, you can certainly have a player who has utility only for one good. And what they will do is whatever their initial endowment is, they'll sell that initial endowment and they will buy as much of that one good as they can with the cash that they have.
The example of a utility function you have as a linear function, which gives some weird results. You can't do 10 stacks of rice and so forth.
So in general, the conditions for equilibrium existing, which was proved by Arrow-Debreu roughly contemporaneously with Nash's proof for basic game theory, the conditions are pretty mild on the utility function. So yeah, you sort of in fact, I'm not even sure you need that. You might be able to substitute other conditions, but certainly that, sort of a smoothness plus monotonic increasing in each variable that would easily do it. And then there's other complicated subsets of weaker constraints which will also give you the result. Okay. Okay. So yes.
So according to that definition, given a network, it's possible that you cannot find a price that is equilibrium.
No. So the basic theorem of Arrow-Debreu says that in the setting that I've described right now, there will always be an equilibrium. There will always be a set of prices at which this magic happens. I'm not talking about finding it, but there always exists a set of prices where everybody essentially can sell all of their initial endowment at those prices. They get P.E cash back. With that cash, they're able to go out and find in the market of sold endowments exactly the bundle of goods that they want to take away to maximize their utility budget and their utility subject to the budget constraint, and everybody can do this. So it's essentially like, the prices are posted, we all dump our stuff into the middle of the table, and we get back the P.E cash. Now we then go buy stuff from the table, and magically, nothing's left on the table. And furthermore, and we've all spent all of our money. Okay? It's actually an amazing result. When we sort of get into the technical details, it's a very beautiful, remarkable result. Sort of 100 years in the making in some sense. Okay, so that's the basic background.
This doesn't say anything about satisfaction, right? It just means I maximize my utility when I bought it, but not that I had enough water.
Right.
Because you might start out with no resources, for example.
Right.
For instance, right.
There are no morals in economics, right? This is not a model designed to take care of people. It's designed to say that the market will function efficiently, but it's not a model of sort of social welfare in any sense.
But you're not going to decide first what you want to buy.
Huh?
You're not going to decide first what you want to buy.
No, you're going to sell your stuff and get cash, and then you're going to see what the best thing you could buy with your cash is. And that might be affected by how much cash you have.
Yeah, but before going in, you know the price of what you want to buy, because that's
Right. So you basically do know ahead of time what you're going to buy, because you know at equilibrium you're going to be able to sell all of your endowment, so you can predict how much cash you're going to have, and then you'll know what point you'll choose to maximize your utility subject to your budget constraints.
That is satisfied.
I suppose you could also have utility for cash, right?
Okay, that's that's kind of a can of worms. So I mean, actually cash,
Because in case later,
I have to admit, the more one thinks about money, which I don't advise, the more of a weird construct you realize that it is. Because cash is supposed to be one of these things that nobody has any utility for per se. And I mean that I don't mean that in this. I mean, obviously having money lets you, but nobody has value. Cash has no intrinsic valuation to anybody, except insofar as it lets them, the more of it you have, the more things you can exchange it for. And so in general, in most of these models, you sort of don't think of cash as something that anybody has utility for. Cash is just kind of a liquidation mechanism to do, among other things, get rid of these pairwise exchange rates between different commodities.
Sure. But if you have time-varying utility functions, then you might temporarily want to have cash because of its expected future.
Sure. Right. Absolutely. Okay, so let me quickly describe a network version of this, right? So we're still going to begin with the same framework. We have K goods or commodities available. We have N consumers, each with their own private endowments and utility functions, just as before. But now we're going to assume that there's an undirected network dictating exchange. So in the model that I've been describing so far, to make things work out, it really had to be the case that we all had a centralized market. We could all dump our goods in the middle. So basically any pair of people can buy and sell from each other, okay? So I, of course, in the same vein as I've been discussing, want to model settings where, for a variety of reasons, certain exchanges are forbidden. So each vertex is now going to be a consumer. There's going to be an edge between consumers I and J if they're free to engage in trade, and no edge between I and J means that direct exchange is forbidden. Okay? And so what's essentially going to happen, let me skip this. This is somewhat of a technical detail. Basically, what's now going to happen is that when you decide that you want to buy rice with some of the sale of your initial endowment, there's going to be multiple. You're not going to be able to buy rice from anyone, but there'll be a local neighborhood from whom you can buy rice. And if there's variation in price between the prices being offered, we're going to add on to the condition of rationality that you're going to buy at the minimum price. Right? There's no reason that you're going to buy rice from somebody who's charging a higher price than a price that's available to you. So one of the things that we're trying to capture in this model is the idea that one of the ways in which variation in price can arise in commodities is purely due to network structure effects. Namely, that you have some network and that some parties might be in a better position in that network than other ones, and therefore, let's say, might be able to charge a higher price for the sale of higher price for rice from the sale of their endowment than somebody's that's not in as good of a position. Okay.
This is not sequential. I mean, could I have utility for rice because I know my neighbor wants it and I'll be able to sell it to him even though I don't.
So this is not.
You
can look at variants of that, but the simple case I want to look at here is where you might think of this as the one-shot game. There's not going to be repeated rounds of exchange, but there's just one shot. You can only buy from and sell to your neighbors. If you're buying, you're going to buy at the cheapest price available to you in your neighborhood. Okay. Okay. So it's not hard to convince yourself that if you sort of take the Arrow-Debreu model and sit it down on a network in the way that I've described, that you can easily create examples. So first of all, equilibria still exist, by which I mean there's still a set of prices for goods, but now there might need to be local variation in prices that has the property that everybody can sell all of their initial endowment at those possibly varying prices. And with the cash that they get, they can basically buy back something from their local neighborhood, only buying from the cheapest prices available to them, some package of good which maximizes their utility, subject to the amount of cash they got from the sale of the endowments. It turns out that that's actually not nearly as easy to prove as I thought it would be when we first had the idea for the result. But after great technical pain, the dust settles, you can kind of recover this result, which is sort of one of these horrific results from a mathematical standpoint that's really difficult to prove, but is one of these things where people that are familiar with the original literature have sort of just assumed that it must be easy to show. Sort of like the worst possible spot to be in from a
So now there's a price plus an equilibrium.
No, so think of the prices being at the vertices. But so basically, when you think about the sale step of endowments, every player is going to essentially advertise prices at which they're selling each of their goods from their endowment, and you and I might be charging different prices for rice.
Okay, so my buying price is decided by your selling price, and everybody's listing selling price.
Yeah. And so let's imagine, let me just simplify this and actually look ahead a little bit to the thing that I'll try to finish this up in the next few minutes or so. But let me just demystify this a little bit. Imagine that there are just two goods, and let's call one of them cash and let's call the other one wheat. And that let's imagine that there's two types of parties in the networks. There's buyers and sellers. And basically buyers all start off with $1 of cash, and sellers all start off with 1 unit of wheat. And everybody only has utility for the opposite good. So buyers essentially have no valuation for their dollar. They only want to trade it for as much wheat as they can possibly get. And sellers who start with wheat don't care about wheat at all. They just want to get rid of it for as many dollars as they can get. And so imagine that you have essentially some kind of bipartite network structure now, because it makes no sense for two buyers to want to talk to each other. They can't help each other. So you have a bipartite network of buyers and sellers and some structure about which buyers and sellers can engage in exchange. So here's some intuitions about why interesting things might happen in this model. So first of all, by the way, this model is deliberately set up so that the only asymmetries between players are really due to their position in the network, right? We're all really symmetric, okay? Especially if I make sure that we're half buyers and half sellers, okay? So to sort of look ahead to what some of the interesting things that can happen in this network, well, if I'm a seller, all other things being equal, it stands to reason intuitively that I would like to have high degree. I would like to be connected to many buyers so that there's as many different parties that I might sell my unit of wheat to as possible. But actually, it's a little bit more subtle than that. Because what I really would rather have than just having high degree is having high degree to a lot of buyers that in turn have low degree. In fact, in particular, I would really like to have high degree to a bunch of buyers that have degree 1, i.e. they can only buy from me. In which case, if there are D of them, I can say the price of my 1 unit of wheat is D dollars, and they have no choice but to each fork over $1 to me and get 1 over D units of my wheat back in return, okay? So there are these sort of subtle effects, and one of the things that we're quite interested in is what is the relationship between that underlying structure of the network and properties like how much prices will vary. I mean, as an example of one of the things that I think we're just figuring out in the last few days, to sort of show you how fresh this is, and then I'll end with a little experimental example. It seems that basically a sufficient condition to guarantee that there will be little or no price variation in such a network is that the graph have an expansion property, which is a very classical notion, combinatorial notion in graph theory, which says that any set of vertices, if you look at it, the neighbors of that set of vertices is larger than the original set of vertices. And this is this is something that's been used in de-randomizing algorithms and all kinds of things in stochastic processes, but it makes a lot of sense from an economic standpoint, right? Because if you don't have expansion properties, that means that there's some large set of vertices that has only a small set of neighbors and is therefore kind of a captive audience of that small set of neighbors, as in the example I just gave. So there's very rich kind of combinatorial relationships between entities like expansion and economic quantities like price variation. So, yeah.
Just follow up. Have you looked at random graphs and the expected values of these kinds of graphs?
Yeah, so one of the reasons I came to this observation is just that I'm trying to prove that in a random graph, that essentially you won't have price variation. Whereas in other models of graph generation, like those mentioned in social network theory, like preferential attachment models, if you're familiar with those.
So random graph, I meant any of these models.
Oh yeah. So so the interesting thing is that there's going to be differences between these models, and so like in a truly random graph, I basically think you can't get price variation. Whereas I think in things like preferential attachment, you can get serious price variation, at least in certain regimes of the parameters. But so let me wrap up now. Just I want to go through this last little example because I worked really hard for a few hours yesterday to get these results just so I could show them to you. So this is an example of a kind of interesting empirical experiment along these lines. The United Nations actually has a very rich site where you can download various repositories of foreign exchange data. In particular, you can get for 120 or so sovereign nations pairwise how much exchange went for, how much import and export went from country A to country B for all pairs of countries A and B. So it's 17,000 entries or something. And there's a number of reasonable ways that one could extract just a pure network structure from this data, and I'm just going to describe one of them right now. So all I did to create this graph was, and I'm only showing, I didn't want to show all 121 because the plotting routine I had would make that very difficult to read. This probably is already bad enough. I'm just showing some of the larger import-export sovereign nations. And all I did to get this very discretized graph from this numerical data is I basically took each country and I gave it a fixed number of links, or a fixed number of votes, if you like. So each country gets to vote for its exchange, for its 3 biggest exchange partners in terms of foreign trade. Okay, so each country, basically, you look at its ranked list of exchange partners and you take the top 3 and you create 3 links from that country to each of those 3 parties. So basically, in the overall graph, every vertex is going to have at least degree 3. But some of them, of course, that are getting lots of votes from other parties are going to have much, much higher degree. Okay? So you can basically get a network structure out of this, and you can kind of see some of the expected things here. So in particular, the USA has a very, very high degree. Japan is in here somewhere, has a relatively high degree. Germany has a pretty high degree. And then, you see the sort of countries that are smaller or have been arranged in the graph more on the outlying edges and have smaller degrees. But so, this is just meant to extract some reasonable network structure from this numerical data, okay? And then what you can do is you can essentially do an experiment of the kind that I described before, where you have total symmetry in the network, and you have some parties that are buyers and some are sellers, and you can compute what the prices commanded at equilibrium for the commodity are for each one of these countries, based only on, so now we're basing this only on the network structure, right? So I've stripped away everything but this network structure, and I want to see if we now compute equilibrium prices, what are the predictions? If we use this as a measure.
So I thought Slovakia has only 2.
Okay, so the reason Slovakia only has 2 is because I'm only showing you part of the graph, so its third partner is one of the ones I'm not showing you.
Checks out.
Yeah, right. Okay.
What are the example countries?
So it's really this model where everybody's either a buyer of, or seller of some good. So some parties start with $1, some parties start with 1 unit of wheat. You only have utility for the other good. You just want to sort of...
And you decide buyers versus sellers from the contract data?
So no, actually that I did randomly. So you sort of do multiple trials in which you randomly assign roles of buyers and sellers. But it's actually entirely, if you think about it, it's entirely symmetric, right? Because, so this randomization step is in some sense unnecessary, but the software we have right now, because I could just call wheat dollars now and dollars wheat and
right, but then there's a question of whether a given link has 2 people of the same kind or of opposite kinds.
okay, so for that, right, so for that I could just ignore the links. But the way I did it was to actually lay down random assignments of buyers and sellers. You throw away the links that aren't useful to anyone because they connect a buyer to a buyer or a seller to a seller, and then you work on the resulting graph to compute the equilibrium. And you do this many times and then look at the average equilibrium price that each country is getting. Okay, so some visualizations of what happens. So if you do what I said, which is you take the graph in which each party gets to vote for 3 other parties, and that's the resulting network. This is showing the assorted bar plot of what the prices are. So for instance, unfortunately you can't really see what the scale is here. So basically, intuitively, because supply is approximately meeting demand, anything over $1 here is sort of a relatively favored country, and anything under $1 is a relatively unfavored country. If you could see the scale which is being clipped off here, you'd see that, first of all, you're seeing this very interesting standard heavy tail distribution, and essentially the country that it's at the top here is the USA, and basically at equilibrium, the US on average is charging 508, Germany is second at 450, then you have Italy, France.
This is the case of the 2. Of the wheat plus.
Yes, right, just this simple case. So, you can sort of compute some distribution of equilibrium prices for this particular network, and you get this particular ranking of the top countries. What I'm showing on this plot is a scatter plot of degree of the vertex on one axis and the price that they're able to charge in equilibrium on the y-axis. And the main point of this is that, in general, there is a monotonic relationship. On a high level, having a higher degree seems to be a good thing, but if you blew up this part of the plot, you'd see that there's a huge amount of variation. So that this is going back to this point that you can't just from the local information alone predict what's going to happen to equilibrium, because these are these second and third order effects having to do with your neighbors. And for instance, there's a this range is going from like 50 cents up to $1.50, which is sort of a factor of 3. Now, an interesting thing to do, of course, is to sort of increase the connectivity of the graph. So one intuition is that as you increase the connectivity of the graph, price variation should diminish, because in general you have more opportunities. So in particular, if you do the same experiment where you, rather than letting each party vote for its top 3 trading partners, you let it vote for its top 10 trading partners, so you get a much more connected graph, then essentially you largely eliminate price variation. So in particular, you're kind of separating the world into the haves and the have-nots, and you sort of see there's a large chunk that are very, very close to $1, maybe a small group that's here that's slightly above $1, and then another sort of group of victims that probably corresponds to these guys with very, very low degree. Now, the natural experiment that was suggested...
Excuse me, and the top is again done by the same algorithm. Everybody...
Yes, everything's the same,
top,
yeah.
Yeah.
Right. Now, the results of this particular experiment I found intriguing, and one of the nice things, I think one of the nice things about having models like this is that you can do experiments, you can do policy experiments, for instance. You can ask what-if questions. Just with Bayesian networks, you can say, what would be the distribution on this object given conditioned on these other events? You can ask similar questions of an economic flavor. And in particular, one interesting thing about the set of results I got here is that it's like, well, the US is getting the highest price here, but there are a number of European countries that are just slightly behind. So you can ask the question, suppose we really treated all of the countries in the European Union as a single entity and basically treated that as one meganode. So it's easy to go modify the data and do the same experiment, this time with the top 3 partners. And so you get this you get this, I'm showing just a fragment of the network here. Here's the European Union, which is kind of condensing some some dozen or so countries in the EU. The US still has a high degree. In fact, the US still has a much higher degree than the European Union. But if you look at what happens, now in fact the European Union at equilibrium will be able to charge on average 465, and the US is second at 360. And in particular, one of the interesting things here is that here is the US with a rather high degree, but considerably lower price than being commanded by the EU. So the prediction here is that if the Europeans could really just stop fighting and get it together, that they would in fact be the new economic superpower, even though their connectivity in this network is below that of the United States. So let me stop there and take questions since I've run over a good bit. Total
globalization.
Well, I mean,
because you don't have any tariffs or anything here.
Yeah, I mean, the way I would put it is that this is a class of models that lets you explore with different degrees of globalization, and you can now, take not just theoretical models of graph generation, but actual networks, and sort of say, well, if we have different thresholds for the importance of links, what are the implications for, let's say, variation in price across, the worldwide prices for a good, for instance. Yeah, we go there and there.
I just had a question. Do you have any early intuitions about how repeated play would affect?
Well, so it depends on how you there are a number of ways of defining repeated play.
In the Axelrod sort of sense, that there's a probability that play will continue.
I see. So you sort of mean local adjustment of spread. So that's a good question. I mean, actually, that's a good question to ask about this before we have the graphical setting. And if you know the literature and learning on games a little bit, which is, as I said, somewhat inconclusive and murky, even less is known about learning basic economic equilibrium. So basically, if you have a model where people are selling and buying goods, and everybody just starts off charging some initial prices for their goods, and then at each round, right, they either sold all of it, and then they might think, maybe I should charge a higher price in the next round, or they didn't sell all of it, so they lower their price a little bit. Very little seems to be known about what are the conditions under which simple dynamics like that of price adjustment would actually converge to an equilibrium. It's a pretty, I want to know more about that area. There's some fledgling literature on it, but it's much, much smaller apparently than the learning and games literature, and possibly harder, unfortunately.
It's easy.
Yeah.
What about phase transition?
Well, I'm not sure exactly what you mean by that, but there are definitely, I suspect that there are a number of cases in which phase transitions occur. So for instance, if you look at a random network model, which is not my favorite model, but it's often one in which it's easy to sort of reason about phase transitions, I'm quite convinced that in the same way that in random graphs, as you sort of increase the density of edges, there are all these properties like, at what point does the graph become connected? At what point does it have a clique of size 17, et cetera? These are all known to essentially have phase transitions, right? That there's a density of edges below which the probability of the property existing is close to 0 and slightly above which it's close to 1. I'm quite sure that in the Arrow-Debreu or random graph model that there's a phase transition in price variation, so that basically there's a density of edges below which you would expect very, very high price variation, just because you're going to, by chance, you're going to have these pockets of victims essentially that are captive audiences of buyers or sellers, and beyond which you would essentially have, as I said before, some kind of expansion property, and then would have minimal price variation.
I was not exactly speaking about perturbation of this thing, but just the very general phenomenon thing, which is that in a graph, if you set up the conditional probability, then it might be that there are several probability on the graph at the limit of this for which you have this given condition. And I don't know exactly what it's linked with the fact that you might have several equilibrium with this, but I'm sure that's true.
Yeah, I mean, the thing that reminds me of is this, in this result on correlated equilibria, the way you actually get in the correlated equilibria and Markov networks, the way one actually gets that result is that, essentially the condition that you have payoff equivalence gives you these constraints on the marginals, and then you actually do a maximum entropy solution of that in order to find the Markov network that will kind of represent the correlated equilibria. Yeah.
In graphical models, there's always this question of structured learning. And so, do you have something similar here? Given, say, a snapshot of price, can you say maybe 2 or 3 snapshots of price? Can you infer the structure?
Yeah, that's a good question. I haven't thought about it. It's sort of on the list of thinking about learning of structure is on. There's a large literature actually in economics on learning structure in games and in economics, but it's actually surprisingly very non-economic in nature. By which I mean that they sort of give up on trying to ask what that would mean with equilibrium added. So it's more things like, okay, it's just some simple dynamics where you have business people and they can do deals with anyone that they come across, and there's some stochastic interaction where either they have a good experience or a bad experience, and if they have a good experience, then they're more likely to trade with that person. So, it's almost just more like a dynamic model of network formation without any economics in it, without any sort of notion of rationality and equilibrium. So there's a large literature on that I should understand better. But I think it would look quite different from the kind of question you asked, which is if you look at a set of prices over time and then reverse engineer what the structure of the graph must be from equilibrium, that kind of inverse problem. I think that's an interesting problem. I don't know what to say about it yet. We're really, much of this stuff, especially on the economics material, we're just figuring out as I speak. So we'll get there eventually, or maybe you will, but it's all pretty nascent.
So let's, if there's one more short question. Okay, well, let's let Mike help you.
Okay, yes, thank you.